This is what we call our metabolic cart. What the cart does is measure oxygen and carbon dioxide concentrations in the air a person breathes out. As the person breathes out, the air travels through a tube through what we call the pneumatic and into the flow meter, where the relative concentrations of these gases are measured. When you burn calories, the reaction uses up oxygen and produces carbon dioxide. By measuring your oxygen consumption and carbon dioxide production, you can determine how many calories you're burning. The nice thing about this particular cart is that it can be used both for exercise and resting tests. So first, I will talk a little bit about how you can use the cart for a resting metabolic rate test, or RMR test. Before the cart can be used, it needs to be calibrated. You first calibrate the flow meter using the large 3-liter syringe, and then calibrate the gas using a standard calibration gas that's designed to be similar to the concentrations in the air you would breathe out at rest. Once everything is set up, the subject lies down on the bed and a hood is placed over their head and tucked in around them. The hood is then connected by a tube to the cart through the pneumatic. All they have to do is relax for the next half hour. It's worth mentioning that the test is best done in the morning before the person has eaten breakfast, so that they are fasted. As I said, the test goes for half an hour, in which the first 10 minutes of data are discarded, because it may take a while for the subject to become fully relaxed. During the resting test, the person is not breathing hard enough to create very much airflow, which causes carbon dioxide to build up in the hood. To solve this problem, we pump air through. The person running the test should make sure to adjust the pump every so often so that the concentration of carbon dioxide stays between 1 and 1.2%. The cart then gives you a report of several different measurements that look something like this. Obviously, in the first column, you have the time in minutes that have passed. In the second column, you have the person's oxygen consumption in liters per minute. In the next column, you have the person's oxygen consumption, this time in milliliters per minute per kilogram of body weight. So you just take their oxygen consumption and divide it by how much they weigh. Next, we have the METs, or metabolic equivalents. And this is calculated by taking your actual metabolic rate and dividing it by your expected resting metabolic rate. We say that a person's expected resting metabolic rate is 3.5 milliliters of oxygen per kilogram of body weight. So what this value tells you is how many times your resting metabolic rate you're currently using. In an RMR test, we would expect this value to be about 1, since you are in fact at rest. In the next column, we have the rate of carbon dioxide production in liters per minute, then the ventilation, which is the total amount of air you're breathing in and out in liters per minute. And then in the next column, we have RQ, which stands for respiratory quotient, and this is the ratio of carbon dioxide produced to oxygen consumed. To understand this, we can look a little bit at the chemistry of the reactions that are occurring when we burn calories. What is happening is we have some sort of carbon compound, usually a carbohydrate or a fat, that reacts with oxygen to produce carbon dioxide and water. Now say that this compound is a carbohydrate, such as glucose, which is C6H12O6. When we balance this equation, we get that for every molecule of glucose that we burn, we need 6 oxygen molecules and produce 6 carbon dioxide molecules and 6 water molecules. What we really care about here is the relative amounts of oxygen and carbon dioxide. Like I said, the RQ is the ratio of carbon dioxide over oxygen, so in this case we have 6 carbon dioxide for every 6 oxygen, and our RQ is 1. So you can see that when you're burning purely carbohydrates, you have an RQ value of about 1. Now let's go back to the reaction and say that our compound is a fatty acid. And fatty acids look something like this, a long chain of carbons and hydrogens ending in a carboxylic acid group. Notice that fatty acids contain much less oxygen in comparison to carbon than carbohydrates. Now if we take this fatty acid, which is C18H36O2, and balance our equation again, we get 18 carbon dioxide molecules for every 26 oxygen molecules, giving us an RQ value of 18 over 26, which is about 0.7. What we can tell from an RQ value is the relative percent of fat and carbohydrate a person is burning, and you can see that in this little chart. Notice that an RQ value close to 1 means you're burning mostly carbohydrates, and an RQ value close to 0.7 means you're burning more fats. The chart then allows you to determine the types of calories a person is burning for an RQ value somewhere in between. As I said before, you can't determine calories being burned just from the amount of oxygen consumed. But if you know the carbon dioxide produced, you can find the RQ, and this chart then tells you how many calories you're burning per liter of oxygen for that given RQ. Notice that you burn more calories per liter of oxygen for carbohydrates than for fats. Going back to our report, we have FeO2 and FeCO2, and these are just the concentrations of oxygen and carbon dioxide in the air that a subject is breathing out. and can be used to calculate the person's oxygen consumption and carbon dioxide production by comparing them to the concentration in the room in the air in the room. In the next column, you have the heart rate, that is, if the person is wearing a heart rate monitor. And then in the last column, you have the REE, which is your resting energy expenditure. And that's often used interchangeably with the term RMR, or resting metabolic rate. And this is what we're really after in the test. It tells you how many calories you're burning, measured in calories per day. So basically, if you sat like this for an entire 24 hours, this is about how many calories you would burn. As I mentioned, this particular cart can also be used for exercise testing. However, there are a few differences in the setup from an RMR test. First of all, we use a slightly bigger pneumatic since obviously a person breathes out more air while exercising than at rest. We also calibrate it slightly differently. We use the same 3-liter syringe, but we use a different calibration gas with a lower concentration of oxygen and a higher concentration of carbon dioxide, and this is more similar to the concentrations in the air one would breathe out while exercising. For this kind of testing, the subject uses a mouthpiece or a mask designed so that they breathe in air from the room and the air they breathe out is sent through the tube to be analyzed by the cart. They usually wear a heart rate monitor that is strapped around their chest. One of the most common and well-known exercise tests is the VO2 max test. A person's VO2 max is the maximum amount of oxygen their body can consume for every kilogram that they weigh. We measure it in milliliters of oxygen per minute per kilogram of body weight. There are several ways to test and estimate a person's VO2 max, but I will just show you how it's done using this metabolic cart. How the test works is the subject starts out running on the treadmill for a few minutes at a moderately easy pace. After that, every 60 seconds they are given the choice to increase the speed of the treadmill by 0.5 miles per hour or increase the grade or incline by 2.5%. Usually the subject will be asked to rate their effort on the RPE, or Rated Perceived Exertion Scale. This scale rates exertion from 1 to 20, with 20 being maximum exertion. The person continues like this until they reach a perceived exertion of 20 and they feel they can't go any harder. Needless to say, this is not nearly as enjoyable as the resting test. While the subject suffers, the cart measures their oxygen intake and CO2 output and gives us a report of the following measurements. A lot of these are very similar to what we would get during an RMR test. First off, it gives the person's oxygen consumption in liters per minute, then oxygen consumption in milliliters per minute per kilogram of body weight, and this is important because the maximum value of this measurement is a person's VO2 max. We also get metabolic equivalence again, which, as you might remember, is the rate of calorie consumption divided by the estimated resting metabolic rate. And unlike in a resting test in which the MET value should be close to 1, during an exercise test, this value increases as the person exerts more and more effort. Next is carbon dioxide production in liters per minute, then ventilation, so the volume of air the person is breathing in liters per minute. And the next measurement, the RER, in exercise testing is very similar to the RQ in RMR testing. It's also the ratio of carbon dioxide produced to oxygen consumed. However, it cannot be used as well to predict the relative amounts of fats and carbohydrates being burned, and this is mainly because when a person exercises, their cells begin to use anaerobic processes to burn energy, and as a result, you can see the RER value often goes above 1. Next, we have RR, which is respiratory rate, and it's the number of breaths the person takes per minute. And then we have tidal volume, which is the amount of air in liters the person breathes for every breathing cycle. To fit the last few things together, if you take the tidal volume, which is the volume you breathe for each breath, and multiply it by the respiratory rate, the number of breaths per minute, you would get ventilation in liters of air per minute. We also have the percentages of oxygen and carbon dioxide in the air being breathed out, the heart rate of the person if they are wearing a working heart rate monitor, and in this case, this person was not. And then we have the total calories burned during the test. So, one problem with this type of VO2 max test is that the subject may quit before they reach their actual maximum oxygen consumption. However, there are a few indicators of whether the measured VO2 max was really the max. Let's take a look. Here we have a graph of my oxygen consumption per kilogram of body weight during a VO2 max test. You can see that it reaches its maximum value before the end of the test and then plateaus. This is a pretty good indication that the maximum value was my actual VO2 max. Another indication of a reliable VO2 max is an RER of more than 1.1. In this case, my RER got up to a max of 1.24, So again, this indicates that we got my actual VO2 max. Another indication is a heart rate within 10 beats per minute of the predicted maximum for that person's age. You can predict your maximum heart rate by taking your age, multiplying it by 0.7, and subtracting that number from 208. The heart rate monitor I was wearing was not working, but we can predict that my maximum heart rate is about 195 beats per minute, and so if my heart rate was over 185 beats per minute, we would have another indication that I reached my full VO2 max. One final consideration with VO2 max tests is altitude. VO2 max decreases about 8 to 11% for every 1,000 meters in altitude above 1,600 meters. Since this lab is at 7,200 feet elevation, which converts to about 2,200 meters, we can say that a person's VO2 max would be about 5 to 7% lower here than at sea level. Therefore, a VO2 max of about 51.6 tested in this lab would be approximately equivalent to a VO2 max of 55 at sea level. RMR and VO2 max tests are some of the most common things that can be done using the cart, but there are just a few examples. There are many other types of exercise tests that can be done on the treadmill, and you can even experiment with things like ab workouts and yoga using the cart. Really, if you want to get creative, the possibilities are pretty much endless.